Good afternoon. I'm Matthew Onoi, computer science students. Welcome to my part, that is Fermat's little theorem. So first of all, we shall study by definition of Fermat and how it is studied. It's a fundamental result in a number theory named after a mathematician called Pierre de Fermat. The theorem states that if P is a prime number and A is any positive integer not divisible by P, then A power P minus 1 is equals to 1 modular P. In layman language, or in other words, if you take any positive integer A that is not a multiple of a prime number P and you raise it to power of P minus 1 and then divide the result by P, the remainder is always 1. Let's take the example below and let's clarify that. So for example, let's say P is equals to 7 and A is equals to 3. Then 3 power 7 minus 1. Remember that 7 P's we have started with P. So 7 minus 1, which is equals to 3 power 6, which is equals to 729. 3 power 6 is 729. If we divide 729 by 7, the remainder is going to be 1. Therefore, 3 power 7 minus 1 is equals to 1 modular 7. So Fermat's little theorem has many important applications in cryptography, such as like in the construction of public key encryption algorithms, which are widely used in modern communication system. Thanks for watching. Have a blessed evening.
Yes, good afternoon. My name is Alex Mageto. I'm a computer science student. So I'll handle this part here on check digits. A check digit a check digit is basically a digit added to a numerical sequence, which is calculated based on the other digits in the sequence. To check the digit, the check digit is designed in such a way that it can be you can detect some common errors that can occur when entering or transferring data. These errors are such as the errors of omission. So check digits can be used in a variety of applications, such as credit card numbers and ISBN codes for books and postal codes. We have an example here. So to check whether a digit code should be ISBN, let's take an example of this code here: 0412606100. Here's the solution. We first label the digits from A1, A2, A3 all the way to A10 in a reverse order, and evaluate A1, 2A2, 3A3, so the summation of all that until 10A10. So considering our code here, A1 will be this, our last digit here is A1. So we'll start with A1 or summation of A1. Then A2 is the second digit here, which is 0. So it will be 2.0 plus 3.1 plus 4.6 in reverse order all the way to 10.0. When we add the sum of these integers, we are going to find 3 plus 24 plus 36 plus 14 plus 8 plus 36. When we simplify modulo 11, we are going to find 3 plus 2 plus 3 plus 3 plus 8 plus 3. So we'll find that the answer is 22. So 22 will be 0 modulo 11. So our code here satisfies the ISBN congruence check. Thank you.
Okay, welcome to the third part. I'm Yusuf Wanjala. I'll take you through multiplicative inverse. Multiplicative inverse is also known as reciprocal. It's a number that when multiplied by a given number, it results to 1. Then let's take this example. We have 3. The inverse of 3, we will just take 3, then multiply by 1 over 3, which will result to 1. Then this concept of multiplicative inverse is applied in algebra, calculus, and number theory. In terms of division, when we divide a number, we are essentially multiplying the first number by its reciprocal of the second number. Let's take, for example, we are taking 3, then dividing by 4. We shall just take 3, then multiply by the reciprocal of 4, which is 1 over 4. Then the results will be 3 over 4, which is the exact reciprocal of the input. Then not all numbers have a multiplicative inverse. Only non-zero numbers have a multiplicative inverse. Some numbers have more than one multiplicative inverse. For example, let's take 2 and negative 2. The inverse of 2 will be 1 over 2, while that of negative 2 will be negative 1 over 2. Then let's take, for example, we are using a fraction down. We are using 7 over 9. While multiplying 7 over 9, the reciprocal of 7 over 9 will just be 9 over 7. And that's my presentation.
Thank you. I'm going to handle the next part, which is linear congruence. My name is Mageto Alex once again, computer science student. So basically, linear congruence is an equation of the form ax is equivalent to b modulo n, where a, b, and m are integers and x is an unknown integer. So this x is the integer that you are interested in. I'm going to show you how we are going to solve for that. The notation a is equals to b modulo n means that a is congruent to b modulo m, which means that a and b leaves the same remainder when divided by m. So to solve a linear congruence, we need to find all the values of x that satisfy the equation. We're solving a linear congruence when a and n are co-prime and n is less than or equal to 13. So we are going to solve the congruence below. 11x is equals to 7 modulo 8. Here is our solution. So first of all, we are going to simplify the linear congruence by replacing the last residue of 11 modulo 8. So since 11 is equivalent to 3 modulo 8, An equivalent linear congruence is 3x is equals to 7 modulo 8 because 3 is our remainder from our congruence here. So check that this linear congruence has solutions. So we are going to as 3 and 8 are co-prime. So this is our guiding principle to check for the linear congruence. So this linear congruence has solutions. We are going to try the values 1, 2 and 3 one by one until where we will find the solution. So we'll start by multiplying 3 by 1, which is 3 mod 8. We have 3 by 3, which is 9. We are going to find 1 modulo 8. So 3 by 5 is 15. So we'll find 7. 7 is our remainder, 7 modulo 8, all the way until where we are going to ascertain that our value here n is less than or equal modulo 13, is less than or equal to 13. We'll determine that by finding x, which is 5. So 13 minus 8 will remain with 5, which is 5 modulo 8. So the solution are given by x is equals to 5 modulo 8. That's our answer. Thank you.
Welcome again in my second presentation. For the purpose of records, Onoi Matthew, a computer science student. We happen to be only 3 in our group since the other member decided to move away. So let me get direct into what I have for today. That is affine cipher. So affine cipher are a type of encryption technique used in number theory and cryptography. So they are a substitution cipher that uses a mathematical function to transform plain text into ciphertext. As we know that plain text is unencrypted. It is an encrypted form which you can view. And then a cipher it is in encrypted form, so it needs to be decrypted so that the receiver can see it. So in a fine cipher, each letter in the plain text is first mapped to a numerical value using a symbol mapping, such as A is equals to 0, B is equals to 1, and C is equals to 2, and so on. The numerical value is transformed using the following mathematical functions, where C is equals to, in bracket, M times P plus P modulo M, where C is the numerical value of the ciphertext letter, P is the numerical value of the plain text letter, A and P are the encryption key parameters chosen by the sender. Then M is the size of the alphabet, usually 26 English alphabet. So the encryption parameters A and B satisfy the condition that A and M are co-prime. That is, they share a common factors other than they, in order to ensure that every letter in the plain text can be uniquely mapped to a letter in the ciphertext. To decrypt the ciphertext, the following function is used. P is equals to, open the bracket, C minus P, then you close the bracket, A n minus 1 modulo M, where a power n minus 1 is the multiplicative reverse of an modulo m